derivative. I remember when we used to say that the derivative was defined at the point. What we will see in this video is that it is itself a function. How do I calculate it? By taking the limit, of the difference quotient of the function. So dry your tears, I say. Oh, derivative. Oh, derivative. Alright, that was a long song, sorry I got carried away. But what we're going to see in this video is the definition of the derivative as a function itself and how to evaluate it from the limit of the difference quotient. Okay, so now that we know how to evaluate limits, let's go back to the definition of derivatives. So recall that the derivative of a function f of x at the point x equals to a is defined as being the limit as h goes to 0 of the difference quotient f of a plus h minus f of a divided by h. And we've seen two important interpretations of this derivative. First, it calculates the instantaneous rate of change of the function at x equals to a. And in the context of kinematics, if the original function was the position function, that calculates the instantaneous velocity. But also there's a geometric interpretation as calculating the slope of the tangent line to the graph of the function, so y equals f of x at the point x equals to a, y equals to f of a. So if I sketch the graph of an example function, so let me pick the function as being x squared. So its graph would look like something like this. So that's the function x squared. And if I pick a point x equals to a and the corresponding point on the graph, I can sketch the tangent line here, and the derivative at this point would calculate the tangent line, the slope of the tangent line at this point. All right, but is there anything special about this a? Well, of course not, right? I could pick any other a, so say x equals to a here, and again the derivative will calculate the slope of the corresponding tangent line. And similarly, a could be here, derivative will calculate the slope of the tangent line. So you probably see where I'm going. So I can basically now define a new function, which I will call the derivative function, which will be exactly such that its value for any x equals to a will give me the slope of the tangent line to the original function. Right, so let's see how it looks like in this example. So let's start at x equals to 0. So the tangent line here is horizontal, so the slope is 0, so my derivative function will take value 0. And if I go on the positive side, then you see that the slope of the tangent line is always positive and increasing, and in fact, you can check, it increases linearly in this case. So for a bunch of x equals to a, I would get something like that. And on the negative side, then the slope is negative and increases in exactly the same way. So my derivative function in this case would basically be a line going through the origin, and it turns out that in fact it will be just a line y equals to 2x, which we will show very soon. Okay, so this is very cool. How can I define that mathematically? So how do I define this derivative function, which is such that its value gives me the slope of the tangent line of the original function? Well, I define it just as above. So the derivative function f prime of x is equal to the limit as h goes to 0 of the derivative quotient, of the difference quotient. Right, so for any x equals to a, this will give me the derivative that I had above. So it seems like I haven't done much here. I've just replaced a by x. But it's quite important. Here a was a point, x equals to a. Here I'm defining a new function out of my original function f of x, which is what we call the derivative function. All right, so before we actually work on examples, there's two comments I want to make. First is just a bit of notation. So there's many different ways we can denote the derivative. Well, one is the one above, so f prime of x. We could also write df dx, which is Leibniz notation. If we use the standard notation that y is equal to f of x, we could also write y prime or dy dx, or sometimes we also write d dx of f of x. All of these notation mean the exact same thing, namely the derivative function. So that was my first comment. The second one is actually quite subtle. When we define the derivative f prime of a here, well, this is only defined here if the limit is actually well defined, if the limit exists, right? It could happen that the limit does not exist here. Either it's the two sides are different, or it blows up to infinity. So the derivative is only defined if the limit exists. So what that means is that the derivative function here could not be defined at some points. So it may happen that the domain of the derivative functions is slightly smaller than the domain of the original function. So in fact, we'll see that in some examples. Okay, so that's all very cool. But here, how did I know that the derivative function was 2x? Started with a function f of x squared, f is equal to x squared. How did I know that the derivative was 2x? Well, that's exactly what we're going to see next. Okay, so what we will do now is calculate the derivative of simple functions using the definition as the limit of the difference quotient. So let me start with the function f of x equals to x. So let's see what this function is. Well, this is a very simple function. It is defined for all real numbers, so in interval notation, the domain would be from minus infinity to infinity. And since it's my first example, let me sketch the graph of the function to see what we expect for the derivative function. So this is y equals to x. That's a line of slope 1 going through the origin. So what do we expect for the derivative function? Well, for any x equals to a here, the tangent line will just be the line y equals to x again, right? So its slope will always be 1. So for any x equals to a, the slope is 1, so we expect the derivative function to just be the constant function y equals to 1. Oops. But let's calculate that now from the definition of the derivative. So f prime of x is equal to the limit as h goes to 0, the difference quotient f of x plus h minus f of x divided by h. Now I can substitute here f for the actual value of my function, so f of x plus h is just x plus h minus x divided by h. Now you see that the x's cancel, so I have the limit as h goes to 0 of h over h. And I can simplify by dividing upstairs and downstairs by h, because as we've seen when we studied limits, we can assume that h is not equal to 0 inside the limit. So I get the limit as h goes to 0 of 1, which is indeed just 1. So that's correct. That's exactly what I had from the graph. The derivative function is just a constant function 1. And in fact, we see here that the domain of the derivative function is also minus infinity to infinity, is defined for all real numbers. So in this case, it happens that the domain of the derivative function is the exact same thing as the domain of the original function. Okay, so for my second example, let me do the example that we had on the previous slide. So I picked the function to be the function x squared. Again, its domain is the same as before. This is defined for all real numbers. So in interval notation, this would be the domain. And if I sketch the graph here, I'd have less space. Well, we had that before, so we had the graph as being this for the function x squared. And then I claimed in my previous slide that the derivative function should be given by a line, namely the line y equals to 2x. So let's now calculate that again from the definition. So f prime of x here is again given by the same formula as the limit of the difference quotient. So I'm going to substitute right away the function here for the actual function. So I get x plus h squared minus x squared divided by h. Now to evaluate this limit, I need to do some simplification. So I'll first expand the square. X squared plus 2xh plus h squared minus x squared, whole thing divided by h. Now you see that things simplify. X squared minus x squared is 0. And for the two other terms in the numerator, they will have an h factor, so I can pull it out. I get h times 2x plus h over h. Just as before, I can divide upstairs and downstairs by h, because I can assume h is not 0 inside the limit. I end up with the limit as h goes to 0 of 2x plus h. Now remember, this is a limit in h, so 2x is a constant here. So if you go back to the flowchart, that we saw when we evaluated limits. If I just substitute h equals to 0 here, well, I just get 2x, which is perfectly well defined. So for any real number x, so I end up with the statement that the limit here is equal to 2x. And since this is defined for all real numbers, the domain of the derivative function in this case is also all real numbers. So it's the same as the domain of the original function. All right, so this is exactly how you prove my statement that the derivative function for the function x squared is just the function 2x. Okay, so let me do a third example. So I'm going to pick the function here to be the square root function. So this is already interesting because the domain now is not the same. So the square root function is only defined for positive x. So the domain of my function would be 0 to infinity, including the point x equals to 0. And if I sketch the graph of this function, what do I get? Well, the graph of the square root function is something that looks like this. Okay, now I want to calculate the derivative function. So I'll do that explicitly from the definition. So let me recall the definition is the limit as h goes to 0 of f of x plus h minus f of x divided by h. And then I can substitute f for the actual value of my function. I get square root of x plus h minus square root of x divided by h. All right, how do I evaluate this limit? Well, you can go back to the flowchart. If you evaluate at h equals to 0, you get square root of x minus square root of x in the numerator, which is 0. So this is a 0 over 0 case. So the flowchart tells you that you need to simplify the expression somehow. What kind of manipulation can we do here? Well, you see that there's some square roots in the numerator, so we may want to try to rationalize the numerator. So let's see whether that works. So to rationalize it, I'll multiply upstairs by square root of x plus h plus square root of x. And same thing downstairs, so I multiply just by 1. And then what will I get? Well, in the numerator, I'll get x plus h. Cross terms will cancel, minus x. And in the denominator, I'll get h times square root of x plus h plus square root of x. Now you see that things simplify. X minus x is 0, and then I can divide upstairs and downstairs by h because I'm not evaluating at h equals to 0, but taking the limit. So I'm allowed to do that, and I end up with the limit as h goes to 0 of 1 over square root of x plus h plus square root of x. Then we go back to the beginning of the flowchart, evaluate at h equals to 0, what will we get? Here we'll get 1 over square root of x plus square root of x, which is fine. It's well defined, so that's the end point of the flowchart. The result is that the limit is equal to 1 of square root of x plus square root of x, or in other words, 1 over 2 square root of x. Okay, this is cool, but there's something pretty interesting here. Is this function here well defined at x equals to 0? It's not, right? It blows up. So the domain of the derivative function here is basically all positive x except x equals to 0. So it turns out that the domain of the derivative function is slightly smaller than the domain of the original function. So what happens here, if you look at the graph, is that for any positive x, tangent line is well defined. But as x goes to 0, in fact, the tangent line becomes vertical. So its slope kinds of become infinity, which of course doesn't make sense. So this is an example of a function that is not differentiable at x equals to 0. You cannot take the derivative of that function at x equals to 0. It's not defined. And we will study in more detail differentiability pretty soon. But the key point here is just to realize that the domain of the derivative function can be smaller than the domain of the original function. Okay, so let me end this video with a question. So I'm going to draw a little table here that will include everything we've calculated so far. So I'll put here in the first column the function f of x. The second column is going to be the derivative function f prime of x. So the first one we've calculated was the function x, which is just x to the power of 1. And we calculated that the derivative function in this case is the function, constant function 1, which you could write as x to the power of 0. Second one we've calculated was the function x squared, and then we've calculated that the derivative was 2 times x, which could write as 2 times x to the power of 1. Now another one that we haven't done, but you could do, in fact it's a good exercise to do it, just calculate it from the definition exactly like we've done, is the function 1 over x squared, or in other words x to the minus 2. And what will you get if you calculate it? You'll get that the derivative here is going to be minus 2 over x cubed, or in other words, minus 2x to the minus 3. And the last one that we've calculated was the square root of x, which we can write as x to the 1/2. And what did we get? We got that the derivative function was 1 over 2 square root of x, or in other words, 1 over 2 x to the minus 1/2. Okay, so here's my question. Now, just looking at this table and trying to see what pattern is going on, can you calculate or guess what the derivative of a function x to the a for any a will be? So what will the derivative function be in this case?